Comments following up on some conversations. Various people had various questions since yesterday's lecture. So there's a couple things I want to just clarify a little bit. One of them is that for most of these lectures, the lectures are titled The Scope of the Landscape, Supergravity, and String Vacua. Because we're focusing on supergravity and supersymmetric solutions, the part of the landscape that we're looking at is a very flat part of the landscape. It's like if you look east out of the tower upstairs, you see Kansas. It's very flat. The part of the landscape that we're looking at in most of these lectures is a very flat, Kansas-like part of the landscape where the effective potential that Tom was complaining about yesterday is V of phi equals 0 everywhere, which I think perhaps makes it a little more impervious to some of his concerns. At the end, in the last lecture, I'll probably say some things that go a little beyond this, but for the most part, we're focusing on these moduli spaces of supersymmetric Minkowski space string theories where there's really no topography to the landscape. The second comment is that I've been drawing this picture where we have a big set, which I call G, of theories that we don't know how to rule out, and then within that, some set of theories which I call V, which are quote-unquote string vacua. And several people were concerned about what I meant by string vacua. And it's a little tricky, of course, since we don't really have a non-perturbative background independent definition of string theory, which gives us a set of equations whose solutions are just all the different vacua. Of course, we can talk about conformal field theory, which describes some classes of string vacua, but perhaps not others. We can talk about supergravity compactifications, which we believe will describe string theory in certain limits, but we don't really have a unified way of describing that. Really what I mean is here, the sets of things where we know enough about string theory that we can construct something which looks like, once we understand what string theory is, and I'm assuming here that eventually we will have some nice unified definition of the theory. Once we have that definition, these are things that should be vacua of that theory. So these are like points in moduli spaces of solutions of some say scalar field theory with a minimum of the potential along which you have some moduli. One other comment here is that I speak of the different theories in here often as different theories, but of course these often are different points in a common moduli space. So it's a little bit perhaps of a question whether one should refer to them as different theories or just different vacua of the same theory. And I think we still have to understand the theory a little better, partly related to some of Tom's comments, before we can really say whether they're different theories or different vacua. I'm going to be a little loose with the language and just refer to the things here as string vacua or as different theories, which in many cases are related by modular deformation. So hopefully those little comments help clarify some of the framework of what I'm talking about. Any questions before we get going? So last time we talked about 10-dimensional supergravity, and we basically went through the analysis of the possible consistent 10-dimensional supergravity theories. We talked about the two n equals 2 supergravity theories. We talked about n equals 1 supergravity coupled to super-Yang-Mills, and we discussed the fact that there are 6 theories which you can't easily rule out. 4 of them have been realized in string theory, and the other 2 are here waiting to be knocked out. What I'm going to talk about today is the same kind of question in 8 dimensions. I want to ask what kinds of theories are compatible with supersymmetry and gravity from the point of view of the low energy theory in 8 dimensions, and which of those can we realize in string theory. So we'll start by talking about the classification of the supermultiplets in an 8-dimensional theory with supersymmetry and gravity. So I'm going to focus on the minimal supersymmetric theories. There are n equals 2 supersymmetric theories in 8 dimensions. The story is actually fairly similar to what I'm going to tell you, although much simpler. So going to the minimal amount of supersymmetry in each dimension gives us an opportunity to explore the most interesting new features which appear in that dimension. So as we go down, I'm basically going to focus on the n equals 1 theories in 8 dimensions, 6 dimensions, etc. So for the n equals 1 theory in 8 dimensions, we have 2 multiplets. We have a gravity multiplet, which has the usual gauge field, usual graviton, gravitino, the B field. It also has 2 gauge fields, 2 different A mu's. It has a single scalar and some more fermions. There's also a gauge multiplet, and this is what gives 8 dimensions some additional richness and structure beyond what we had in 10 dimensions. In 10 dimensions, there were a couple of possible gauge groups. Here, there is a much wider range coming from this gauge multiplet. Because in 8 dimensions, the representations of the Poincare group involved in this supergravity theory are pseudo-Majorana and not chiral, there are not going to be anomalies, so we do not have strong constraints as we did in 10 dimensions. This is a little bit more like what happens in 4 dimensions, where there are no gravitational anomalies. In 10 and 6, where we can constrain the theories a little bit more, we can make much stronger constraints on the set of possible consistent effective gravity theories. So that's one of the reasons I decided to include the 8-dimensional case here. Yes, Oliver?
Those 2 multiplets, are they the same number of supercharges? Because one looks much bigger than the other.
The 2 multiplets have the same number of supercharges, but different numbers of bosonic fields. Right? Are you talking about the bosonic versus fermionic in one of the multiplets, or are you talking about?
Just count the bosonic degrees of freedom. One has a gauge field, 2 scalars.
Yeah, there are 8 in the bottom multiplet, and there are, I think, there. Oh, yeah, the dimension here is not a power of 2. Actually, there's kind of an interesting thing which happens when you reduce from 10 dimensions to 8 dimensions, which is that you split up the 10-dimensional supergravity multiplet into 2 gauge multiplets. Well, we're actually going to go through this explicit dimensional reduction, and what we'll see is that the gravity multiplet in 10 dimensions splits up into 2 8-dimensional vector multiplets and a smaller gravity multiplet.
Is the issue that one of them is its own CPT conjugate and one of them isn't? So the gauge field, maybe the lower one, you have 16 supercharges. You can get from helicity 1 to helicity -1.
Yes.
If you start from helicity 2, you only get to helicity 0. So then you need to double the multiplet to get the helicity -2 graviton.
That's true, but I don't think that addresses the disparity that he's talking about. I think what he's talking about is more related to the fact that this multiplet is much, much bigger than this multiplet.
Yeah, it's even bigger than that.
It's even bigger than that, yeah.
Yeah.
So it has to do, I mean, they're just, it is not true in every dimension that the representations of supersymmetry are going to give you multiplets which are powers of 2. You get things like 56-dimensional representations and things like that. And that's what we're seeing here. And this has to do with this fact that when we reduce the 10-dimensional gravity multiplet, it becomes a reducible representation of the 8-dimensional supergravity algebra. So that's why, for instance, when we do, I will see this in a minute, but that's why when we do the dimensional reduction, we only get 2 A mu's here, whereas you might have thought you got 4. So if you look at the set of 8-dimensional fields which come from the 10-dimensional supergravity multiplet, that would include 4 vector fields coming from the G and the B wrapped on 2 possible compact directions, but only 2 of them stay in the gravity multiplet. Anyway, I'm not sure that completely addresses your question, but there's some funny things happening with the gravity multiplets here. The main point I want to emphasize is that we do not have strong constraints on these theories, so from the low energy point of view, it looks like any gauge group will do. So the set of possible theories here seems to be infinite. So the question we want to ask is, first of all, how big is the set of theories that we can realize in string theory? And then we might want to know whether those theories we don't know how to realize in string theory can either be ruled out or found in string theory or not. So we want to now address the question of what we can get from string theory to fill up part of this space of possible gravity theories in 8 dimensions. So the 3 things I want to do today to go through this are, first of all, to talk a little bit more about the compactification process. If you take a theory in higher dimension, compactify it, we'll talk a little bit more in detail about what happens in that dimensional reduction process and what kinds of spaces we can dimensionally reduce on. Then I'll talk about 2 particular string theories in a little more detail. First, I'll talk about the heterotic construction, where we can see very clearly what kinds of theories we get in 8 dimensions by understanding a little bit better some of the theory of lattices and compactification of the heterotic string. And then I will introduce some of the ideas of F-theory, which actually are most cleanly introduced in 8 dimensions, where we really fully understand everything that's going on. And we'll see that heterotic and F-theory will give us the same answer for the set of n equals 1 8-dimensional theories which can be realized. This is because these are dual string theories. They are representing the same class of theories in wildly different appearing, from perspectives that appear to be wildly different at first. So today we'll see some more about compactification, more in depth about heterotic and F-theory, and we'll understand how this duality works a little bit. Any questions about the plan? Yes, please.
I'm a bit confused about the number of supercharges in the algebra. There's 16 supercharges in 10 dimensions too.
There are. So this, if you reduce, for instance, if you take a theory with 16 supercharges in 10 dimensions and you reduce it on a torus, you'll get another theory with 16 supercharges. The number of supercharges stays the same if you reduce on a torus, because you're basically taking flat space and just doing some periodic identification. So the set of supercharges or spinors is going to be invariant under that reduction. So we can always get a theory with 16 supercharges in any dimension by taking a theory with 16 supercharges in 10 dimensions and reducing on a torus. So
wouldn't you get like n equals 2 in 8 dimensions?
Well, in 8 dimensions, you only get n equals 1. When you get down to 6 dimensions, you get n equals 2. You have to go, if you look at, again, in Joe's book, there's this nice little table of the representations of the Clifford algebras and the spinor structures. The number of supercharges in dimensions 7 through 10 basically stays the same, and then when you go down from 10 to 6, you drop by a factor of 2. So there are various different properties in different dimensions. You have to look at each case and see what's going to happen when you do that reduction.
So wouldn't we compactify 2A or 2B on the torus?
Then we would get an n equals 2 gravity theory in 8 dimensions. As I said, I'm not going to address those. There are some n equals 2 gravity theories in 8 dimensions. They only have one multiplet, and the structure is much simpler. Basically, they just come from, as you just said, taking 2A or 2B, reducing on a torus. And the same kind of analysis that I'll go through today allows you to give a complete set of those theories. But it's a much simpler set. So I'm going to focus on theories with the minimal amount of supersymmetry consistent with a supergravity theory in each dimension. There are n equals 2 in 8 dimensions, but I'm not going to talk about them. Oliver?
I was just going to make a comment about the previous question about why
Sure.
it's minimal 16 and 10 and 8. So it's true that when you drop 2 dimensions, the Dirac spinor always drops by a factor of 2. But in 10 dimensions, you had Majorana-Weil spinors, which impose actually a factor of 1/4 than the Dirac spinor. So in 10 dimensions, they're 1/4 as small as they could have been. When you drop to 8, you can't have Majorana-Weil, just Majorana. They're only half as big as the Dirac spinor. So the Dirac spinor from 10 to 8 does get half as big, but the minimal thing you can get is the same size because of these shifting abilities to have Majorana-Weil in some dimensions and just Majorana.
Right. That's where the numbers I was talking about in Joe's table come from, is from whether you can have Majorana-Weil, et cetera. And in general, these are periodic with periodicity 4 or 8. And
Shouldn't that be n equals 2 then? Isn't dimension 2 to the 4 minus 1?
no, this is 16 supercharges, so it's n equals 1. Sorry?
The spinor. Isn't, what's the dimension? How many edges does the spinor have?
So the pseudo-Majorana spinor here is going to have a dimension of 16.
The Dirac spinor.
The Dirac spinor is 2 to the 4, complex. But then you have to divide by 2 for Weil, but then multiply by 2 because it was complex and you want to count real supercharges. And then you get 6 times.
Great. Thank you. Yes.
What's the problem in looking at irreducible representations of the supersymmetry algebra in terms of defining multiplets?
Sorry, what is the question? We did look at irreducible representations to get the multiplets.
So you said you had 56-dimensional multiplets?
You can have, yeah.
Yeah, no. But so can you break them into irreducible pieces?
No, that you can have a 56-dimensional irreducible representation.
Okay.
In some dimensions, in particular, in dimension 8, for instance, let's figure it out. Okay. I was punting because I didn't remember whether this was okay. So let's see. So G mu nu. We have 8. So the little group is SO6. So it's 6 times 7 over 2, which minus 1, which is 21. B mu nu has 6 times 5 over 2, which is 15. I'm probably going to do something wrong here. A mu has 6 times 2 is 12. Sigma has 1. 21 plus 12 plus 15 plus 1. I'm sure I've missed something here. Is 33. 20, good. Thank you. 20, that's good because I didn't want that. I want 48. Yeah, so this is 48 dimensional, which makes sense because the 10-dimensional irreducible representation is 64. And when we dimensionally reduce, which we'll do in just a minute, you split off two 8-dimensional representations, which are irreducible, leaving with a 48-dimensional representation. The 56 I was remembering is from 9 dimensions. Sorry, I was thinking for a while about 9 dimensions recently. And so the 56 I had in my mind was the 9-dimensional representation, which has one vector in 8 dimensions by this calculation. We get 48 dimensions in this representation. Adding that to 2 of these gauge multiplets gives us 64, which is the number of bosonic degrees of freedom in the 10-dimensional n equals 1 representation. Okay, so is everybody happy with the numerology now? Okay, it's good. No, it's good that we can get these things correct. In just a moment, I'll actually write down the compactification so we can see how this thing is splitting. But any other questions before I go on? Okay, so before we explicitly do the compactification of the heterotic string, I just want to say a few generalities about what we do when we compactify. We already yesterday saw what happens when we compactify 11-dimensional supergravity on a circle. We get a theory with the same number of supercharges. And the same thing is true in general. If we compactify any theory, any of these supergravity theories, on a d-dimensional torus, we'll get a theory in the original dimension minus d with the same number of supercharges. So that's all very well, but we'd like to be able to do slightly more general things to get a wider range of low-energy theories, not just compactify on tori. So there are lots of things you can do. And for a long time, the main thing that people did was compactify on Calabi-Yau manifolds. And more recently, there's been a lot more interest in other kinds of structure that you can add in. So just kind of briefly, there are the purely geometric compactifications. And we'll talk a little bit more about these in a minute. The classic compactification on a Calabi-Yau, which preserves some fraction of the supersymmetry, as we'll see in a moment. You can compactify 7 dimensions on a G2 manifold. This is a purely geometric compactification. You can add widgets in your compactification, which are carefully chosen to preserve supersymmetry. And one of the widgets that you can add is branes. As Miriam discussed yesterday in her lectures, we can compactify on some space and add some branes with the proper codimension and configuration that they preserve some supersymmetry. And that's the underlying philosophy behind intersecting brane models and in one picture of F-theory. And so we'll talk a little bit about these F-theory today and then more about intersecting branes and F-theory in the following lectures. Another thing you can do is you can compactify on some geometric space and include fluxes. So this is, of course, famous from the flux compactification story in the context of the landscape, which we've already heard a bit about. ADS-CFT is another example of a compactification with fluxes. You compactify and you have ADS5 cross S5. You have some RR flux, which enables you to have this compactification to on a spherical space. You can also compactify with H-flux, which leads to so-called non-Kähler compactifications. And these are another interesting subject of current study. For today, I'll really just be talking, well, at least for the heterotic, I'll talk about the pure geometric. And then when I say something about F-theory, this will be related to the branes plus geometry. Any questions about that? OK, so let's start with pure geometry. We want to take a theory in capital D dimensions. We're not going to turn on any fluxes, no H-flux, no Ramon-Vermon flux. We're going to keep the dilaton constant. We compactify on a k-dimensional space of some kind of geometry, and we get a d minus k-dimensional theory, which we then want to study. So the first thing we want, since I'm really focusing on theories with supersymmetry, is we want to preserve some supersymmetry in this compactification process. So that means that the ground state of the theory after the compactification had better be supersymmetric. That means that, in particular, if the ground state is supersymmetric, then 0, the ground state, and the anti-commutator of the Q of some Q's with any of the operators in the theory anti-commuted in this ground state has to vanish, since Q is supposed to annihilate the ground state. So in particular, if we choose U to be the gravitino, then the variation of the gravitino under supersymmetry, which is given by the covariant derivative of a spinor supersymmetry parameter eta, has to vanish. And that means that in order to preserve supersymmetry, we need to have a covariantly constant spinor on our compactification manifold. So we need to understand what kinds of manifolds allow a covariantly constant spinor to be built on them. And the most famous and well-known class of such manifolds are manifolds with SUN holonomy. If you take a complex manifold of complex dimension n, if it has SUN holonomy, that means that there's going to be a spinor which transforms to itself under any, or if we look at a spinor on that manifold, the holonomy will tell us what happens when we go around some loop and bring that spinor back to itself. That has to be in a restricted subgroup of the total SO2n transformation group in order to have this thing fit together. So SUN holonomy is going to give us a covariantly constant spinor. A clear way to think about this is that the spaces with SUN holonomy are Kähler manifolds, so they have a complex structure. And the complex structure in general will impose a UN holonomy. And the statement that the holonomy is actually SUN means that if you take the U1 in the center of the UN, then that's a U1 bundle. It's got a first Chern class. That's got to have a vanishing, the first Chern class has to vanish, which means that there's no holonomy in that extra U1. So this is one definition of a Calabi-Yau manifold. There was this famous conjecture of Calabi that any compact manifold which satisfied these conditions admits a Ricci-flat Kähler metric, which was proven by Yau, and so hence these are called Calabi-Yau manifolds. So there's a class of manifolds which are distinguished by this characteristic of having an SUN holonomy, and there's various equivalent definitions of these manifolds, and we'll go through a few different examples of these and discuss these in a little more detail as we go through the lectures. I might just mention, if you want to know how to get a Calabi-Yau manifold, a simple way to do it is to write a homogeneous polynomial of degree n plus 1 on Cpn. So for instance, a cubic on P2 gives us an algebraic curve, which is a torus, or an elliptic curve, which is a Calabi-Yau manifold in one complex dimension. If we have a quartic in P3, it gives us what's called a K3 manifold, which we'll talk about a little bit more. And if we have a quintic in P4, it gives us a Calabi-Yau threefold. So we'll talk a little bit about these as we need them. But just to give you, if we look, you can classify manifolds which admit covariantly constant spinors, and the important ones for physics that we in are if we compactify 4-dimension we discussed on a torus, then the holonomy is just 1 because it's just flat. Everything goes back to itself. Okay. If you compactify on, we good? If you compactify on 4 dimensions, which are a Calabi-Yau twofold or K3, then you break half the supersymmetry. If you go down on a Calabi-Yau threefold, you break 3/4 of the supersymmetry down to 1/4, et cetera. Calabi-Yau fourfold, you're down to 1/8. And then there's this exotic case of the G2 manifold compactifying on 7 dimensions, which also breaks 1/8. So what I want to do now is just do an explicit discussion of a couple of these compactifications which we can do to get 8-dimensional theories. So the first one I want to talk about is the heterotic theory, compactified from 10 dimensions down to 8 dimensions. Step back for a second. First, let's ask, okay, given this general picture of compactification, what are all the possible things we could imagine doing to get an 8-dimensional theory with one supersymmetry? So we have a bunch of theories with one supersymmetry in 10 dimensions, the heterotic and type 1. And if we compactify those on T2, we should get an 8-dimensional theory with one supersymmetry. As we'll see, these are all essentially equivalent. We'll talk today about why the two different heterotic compactifications on T2 are equivalent. And soon, perhaps if not today, tomorrow, we'll talk about the connection between type 1 and heterotic. You could imagine trying to do some kind of type 2 compactification with branes or something. But if you try to do this, you realize, which will be clearer after we do some intersecting brane models tomorrow, that basically if you compactify on type 2B or 2A, you have to put in some orientifold to have something which cancels the brane charge, and ultimately you have to put the branes parallel to the orientifold, and that ends up being equivalent to the type 1 compactification. So there's not really anything different you can do with type 2 here to give this kind of theory, except for this F-theory compactification, which can be thought of as a type 2B compactification. And we'll talk about the various ways of thinking about this later in this lecture. This is the second way in which we can get an 8-dimensional theory with one supersymmetry, is by compactifying either 2B on a sphere, if you prefer, or F-theory, which is kind of an imaginary 12-dimensional theory, on a K3, giving us this 8-dimensional theory. And that'll make more sense after we describe F-theory in a little more detail. But so basically, these are the only ways that one seems to be able to take string theory and construct 8-dimensional theories. So what I want to do is go through explicitly how each of these things works and show that we get the same answers and that therefore these things are dual descriptions of the same low-energy physics. Any questions about the game plan? Yes?
So the second thing, the F-theory compactification to 8D.
Yes.
Can be think of it as type.
Okay, there are various duality limits in which you might be able to think of this as a limit of type 2 on a, well, not for a generic K3. There might be other limits which end up being equivalent to some of these things, but I would certainly posit that you will have a hard time finding any other construction which will give an 8D theory which is not equivalent to one of these. The generic type 2 compactification without introducing more complicated structures and exotic limits is not going to give you an 8-dimensional theory.
No, I was thinking of orbifolding. So.
Right, but then if you compactify type 2 on an orbifold K3, then you're down in 6 dimensions, and you have to take a limit to go back to 8.
No, what I meant was orbifolded T squared over T squared by some, I don't know, Z2.
I'm not sure how to, let's talk about that afterwards. I'm not sure how to get a theory that will make sense out of that, but let's talk about that.
You will just get a torus back.
Well, the T2 mod Z2 singularity is resolvable, but yeah, I'm sorry. I'm on the spot. I'm a little confused about that example, but.
There's no two-dimensional manifold that breaks half supersymmetries, just purely geometrically. And if there were a two-dimensional orbifold, it could be resolved into a geometry, and then it would be a two-dimensional manifold that broke half supersymmetry. So if there just isn't such a thing, a torus would still give you 32 supercharges.
Yeah, I mean, whether you can add some gadgets to that. I think if you could find a way of making that work by adding some stuff which fixes up the supersymmetry, I think you're going to be back in this game here. But it's a good. I encourage you to try to find encourage everybody to try to find another way of getting an 8-dimensional theory, and then either show that it's equivalent to one of the things which I'm describing here, or figure out why it's not, and then tell me about it. Okay. So let's do the dimensional reduction of the n equals 1 supergravity, which I've been promising for a little while, and we'll see how this works. So if we take the gravity multiplet, if we look at the G and the B field, G has 2 indices, therefore there are 3 gauge fields we can get. There are 2 gauge fields we can get from G and 2 gauge fields we can get from B by putting one of the indices to be one of the 2 compact directions. So that gives us 4 gauge fields, so that in the compactified theory we get the original 16, because both E8 cross E8 and SO32 are rank 16. So we get 16 plus 4 is 20 gauge fields, giving us a gauge group of G cross U1 to the 4th on a generic toroidal compactification. In the scalar sector, we're going to get the original scalar, which stays in the gravity multiplet. We get each of the A's compactified on a compact direction. There's 16 of those. That gives us 32 for 2 compact directions. And then there's three possibilities here from G. There's 1, 1, 1, 2, and 2, 2, or 8, 9, 8, 8, and 9, 9. For B, we just have B, 8, 9. These guys give us 4 more scalars, so we get 36 scalars. So we can see how this breaks up into a gravity multiplet, which you remember had 2 of these gauge fields, plus 18 vector multiplets, which have all 36 of the scalars and 18 of the vectors. So that was this little story I was talking about at the beginning, where the 64 broke up into a 48 plus 8 plus 8. And Oliver has something else he wants to add.
Why don't we have 252 gauge fields in 8 dimensions? We have 248 in 10 dimensions?
Yes, we do. That's a good point, and we're going to talk about where the other gauge fields went in a couple of minutes. I'm looking here at the ones in, yeah, you're right. I've said this in a confusing way, because in the direct toroidal compactification, we've got these 20, which are the center of this, plus another, 240 of these guys from the things that are not in the center. So you're right. There's a bunch of non-abelian A mu's, which I haven't included here. These are the ones which commute. In a moment, we're going to do a more general way of doing the toroidal reduction, in which we'll see where all those extra gauge fields have gone. But you're right that this way of saying it, it's a little confusing where the extra gauge, where the non-abelian part of the gauge fields went. Okay, we'll see the answer to this in just a minute, but that's a good point, Oliver. So the main thing we can do in this point of view, from this point of view, is we can turn on Wilson lines around the various circles of the torus. We can't turn on fluxes, because if we turn on a flux, that would break supersymmetry. There's you can't turn on a flux on a 2 torus in any way which is compatible with supersymmetry. If we had a 4 torus, we could do a self-dual or anti-self-dual configuration, which would be like an instanton. We might preserve supersymmetry, but not on a 2 torus. We have an energy which goes as f squared. It's going to make it impossible to get any kind of compactification with non-zero flux. So the Wilson lines around the circles have to commute, and these things are then going to break the gauge group to a subgroup of the full gauge group, which is the set of things which commute with the 2 Wilson lines. Yeah, sorry, I'm thinking in the back of my head about Oliver's question. The correct statement is that if we start with the full non-abelian gauge symmetry here, so we have the W fields, et cetera, the off-diagonal guys here, there's a bunch of further gauge multiplets which drop down just as 1, 2s. So we have a bunch of additional, these are the vector multiplets associated with the diagonal part of the gauge group, and then there's a bunch of other ones which also come along for the ride. Sorry about that confusion. We'll see that a little bit more clearly in a minute. So generically, if we just compactify on a torus, it looks like the biggest gauge group we can get is something which is a subgroup of G, which is the commutant of the Wilson lines. But when we compactify the heterotic string, or anything on the torus, there's an additional possibility, which is we can actually enhance the gauge symmetry at specific moduli. And this leads us into trying to understand lattices a little bit better, because lattices, when we compactify on a torus, we're essentially compactifying on flat space modded out by a lattice. And as we'll see, there's a bunch of mathematics associated with lattices which will play kind of a key role in a lot of the constructions we're going to be doing of these lower dimensional supergravity theories. So I'm going to take a little interlude and talk about lattices. But before I do that, are there any other questions here besides the point Oliver made, which is that I've dropped a bunch of the off-diagonal gauge bosons? I'm just saying if you have some flux, the Yang-Mills energy, E is F squared, that's going to break, any F is going to break supersymmetry. That's just one manifestation of that. Other questions, comments? Yeah, so actually the correct thing to put in, let me just actually correct this on the fly. Correct thing to write here should be 4 plus n, where n is the number of generators here, and this is going to be 4 plus 2n. I think that's right. So, yeah, good. So this thing is, if we take this, take off 2 of the gauge bosons and put them in the vector multiplet, then twice that is the number of scalars, so everything works out. So all is well. And once we do this general discussion of tori, we'll be able to understand more generally what the compactification of the heterotic string is really doing, so we can understand how these enhanced gauge symmetries, including SO32 and E8 cross E8, are really arising. So what I want to do now is kind of, if what I just said was confusing, and I'm sorry about that, this is now a more general point of view from which we can understand all of it much more clearly, which is really where I wanted to go through this. So,
What is H on the previous side?
what's that?
What is H on the previous?
What is?
The group that is broken.
This is, oh, sorry, there's supposed to be a set here. This is the H is, the gauge group is going to be broken to the subgroup of G, which consists of all elements of G which commute with A8 and A9. So that's just the commutant of A8 and A9. So H equals the set of H, so that H comma A8 equals H comma A9 equals, what's that? It depends on what you choose for A8 and A9. Generically, it'll just be the diagonals. So generically it's just U1 to the 16. So that's why I started out with the 20. If you choose generic Wilson lines, you're going to get the things I crossed out. But if you don't choose generic Wilson lines, you'll have greater symmetry. So sorry, I jumped ahead when I wrote that to the point where we had broken all the symmetry. The symmetry in H comes from things which commute with the different Wilson lines. So if we don't turn on Wilson lines, we're going to get a much bigger gauge. We're going to get a much bigger gauge group.
And that's what you mean by enhanced gauge symmetry? Or you mean
No, I'm actually going to say more. There's even bigger enhancements. What's that? That's right. So that's why I was being kind of quick and hasty there, because we're going to actually do a more general thing now, which can give us bigger groups than G, and will, among other things, unify the 2 different heterotic strings once we've compactified on at least one torus. So that was supposed to be kind of a heuristic thing before we got to the actual calculation, but since I muddled it a little bit, we got bogged down. Sorry about that. Okay, good. So let's go back to the question of lattices. So again, I just want to give you a little bit of the basics of what we want to talk about in terms of the mathematics of lattices, since they're going to play an important role in a lot of the compactifications we're going to talk about, not just heterotic, but actually almost all the things we're going to talk about tie in some ways to lattices, which is true for these higher dimensional compactifications. It gets more complicated in lower dimensions. So a lattice is basically the set of integer linear combinations of some set of basis vectors. So it's just, the picture here is a picture of a lattice. And in mathematics, a lattice is usually taken to carry a symmetric bilinear inner product. So some dot, which allows you to dot lattice vectors into each other. And the signature of our lattice we're going to denote by PQ. So that dot product is going to have some positive and negative pieces to its signature. Just a few definitions. An integral lattice is a lattice where when we take the dot product between any two vectors in the lattice, we get an integer. An even lattice is one where any vector dotted into itself gives you an even integer. For any lattice, we can define a dual lattice, which is the set of all vectors which, when dotted into any element of the lattice, give us an integer. So just for example, imagine we have the lattice. We can associate a lattice with a matrix, which is the matrix of inner products of the lattice vectors. So let's define a lattice A11, which is just 2. So that's a vector E, where E squared equals 2. So that's an even lattice, because anything in the lattice squares to an even number. The dual of that lattice includes E over 2, because E over 2 dotted into NE is equal to N over 2 E squared, which is equal to N. So this lattice, the blue lattice with E squared equals 2, is not self-dual. The dual lattice has twice as many points in it. Okay? A self-dual or unimodular lattice is a lattice which is equal to its dual. So other ways of saying that condition are if you take the matrix defining the lattice, if its determinant is 1, that's the same as saying that the unit cell of the lattice has volume 1. Either of those conditions is equivalent to the statement that the lattice is self-dual. And there's a convenient theorem, which we'll see some aspects of in a few minutes, by Milner, which says that any unimodular lattice of signature PQ has to have P and Q differing by 8. So in particular, there's no even unimodular lattice in 2 Euclidean dimensions. You can't draw a lattice in 2 Euclidean dimensions which has both the even property and the self-dual property. You clearly see it in 1 dimension, right? I drew an even lattice, and it's not self-dual. If I make a self-dual lattice, it's not even, because we need E squared equals 1. So that's pretty clear. So you have to go up to dimension 8 before you get, in the Euclidean space, a unimodular lattice. So here's an important example of an even unimodular lattice. It's one with signature 1, 1, and we can describe it by the matrix 0, 1, 1, 0. So that means if we have 2 lattice vectors, which are basis elements for the lattice, E1 and E2, E1 squared is 0, E2 squared is 0, and E1 dot E2 is equal to 1. So I claim that that's an even lattice. It's unimodular because the determinant of this matrix is -1, which is plus or minus 1. It's got signature 1, 1, because if we diagonalize it, it's got eigenvectors 1 comma plus 1 and 1 comma minus 1 with eigenvalues plus and minus 1. And the inner product of any vector with itself, generally if we take NE1 plus ME2 squared, that means dotted into itself, the E1 squared part vanishes, the E2 squared part vanishes, it's 2NM times E1 dot E2, which is 2NM, which is even. So this is certainly an even and unimodular lattice. It's an important one. Okay, any questions about that? This may seem a little far afield, but it's actually the key thing we need to understand in order to understand how to compactify the heterotic theory. Any questions? And it'll also play an important role in understanding a lot of aspects of F theory in 6 and 8 dimensions. Okay, so we're all good with lattices. One of the things about lattices which makes them very important for our study is that there's a close relationship between lattices and Lie groups. If we take any of the simply laced Lie groups, that is SUN, SO2N, or E6, E7, or E8, we can take the simple roots of those groups, form a Cartan matrix. So in the normalization where the root squared is 2, the Cartan matrix is just given by the matrix of inner products of these guys. And on the one hand, this forms a lattice. So this gives us some lattice associated with each of these groups. On the other hand, we have this famous Dinkin diagram picture, which allows us to graphically depict the inner products of the various root vectors by representing the roots by a dot and simple roots whose inner product is -1 by a line. So for example, for SU3, we'll just remember that the simple roots are often drawn U, and I think this is often called V. There's a lattice which looks like the triangular lattice, and this is familiar from learning basic quantum field theory. We've learned about SU3 and its representations. The Cartan matrix for SU3 is the inner product matrix of these two basis vectors, this guy and this guy. Each of them has a norm squared of 2. Their inner product is -1, and so we get a Dinkin diagram which looks like this. 2 roots with an inner product of -1 corresponding to the off diagonal. E8, which is going to play an important role, is this guy, which has this Cartan matrix and this Dinkin diagram. So E8 is funny because this picture and this matrix make it look like it's a very non-symmetric kind of thing. But actually, E8 is a really beautiful and symmetric lattice in 8 dimensions. There's another presentation of the E8 root lattice, which we can give by the set of x1 through x8, so that the sum of the xi's is in 2z, and xi is either in z for all I, or xi is in z plus 1/2 for all I. So while it looks like there's some asymmetry between the various roots here, there's this very simple picture of this as a lattice in 8 dimensions where we take all of the points which are either on integer lattice points or on half integer lattice points, that is the integer lattice shifted by a half in every direction, with the property that when we sum all those points, we get an even integer. And so this lattice is very important because I mentioned that we can't have an even unimodular lattice in dimensions less than 8. People have classified the Euclidean self-dual or unimodular lattices, that is with p equals 0. They only appear at dimensions which are multiples of 8. And the first one is the E8 root lattice. So this lattice here is the first even unimodular lattice in Euclidean signature. When you go up to dimension 16, there are 2 even unimodular lattices. One of them is 2 copies. That should be an O plus as a lattice, right? The group is E8 cross E8. Its associated lattice is E8 plus E8. And there's a second lattice, which is even unimodular, which is lambda 16, which is closely related to, though with an extra copy shifted by a Z2, associated with a Z2 in the gauge group, there's an additional copy of the lattice added with a shift, which is lambda 16. So there are 2 distinct even unimodular lattices in 16 dimensions. And then when you get up to higher dimensions, the story gets even more complicated. In indefinite signature, the story is much simpler. So this is actually a kind of a theme which is going to come back at various times. If we have an indefinite signature lattice, life is very simple. It's always a bunch of U's plus a bunch of E8s. So basically, any even unimodular indefinite signature lattice is going to be represented as a bunch of these U guys that we had on the previous screen, this thing, plus a bunch of copies of E8. Okay, that's the end of the interlude on lattices. Any questions about all that? I just wanted all the roots to have the same length and all the inner products to be -1. There are other kinds of groups which have other kinds of inner products. They get more complicated.
Right, but so where'd that come into the lattice side? That's what you wanted, or you wanted it to be modular? I guess my question is it a
Yeah, good. So the lattices which we associate with the non-simply laced groups, let me think about that for a second, because the gauge symmetries appear in a more complicated way for the non-simply laced groups.
The Cartan matrix for those groups is not symmetric. So if this is a matrix inner product, does it mean that you're...
Yes, good. Good. Thank you. I think it was, yeah, it's the fact that the Cartan matrix is not symmetric. Thank you very much, Oliver. Oliver bails me out again. Good. Thanks a lot. That is absolutely correct. So the point is we want a lattice, and although you can form a Dinkin diagram, which then you can describe with these various different kinds of double-edged and triple-edged things, you're not going to get a lattice with a symmetric form, as Oliver pointed out. Good. And the physics manifestation of that is that to get those gauge groups, you have to do more complicated things. So, for instance, we'll talk probably later in the week about how in F-theory you can get some of the non-simply laced groups by introducing monodromies or quotients in the F-theory picture, but it's not through such a simple such a simple kind of construction as this. The only kinds of groups we're going to get directly through this lattice construction are going to be the simply laced ones. Good. Other questions? Okay, so how do we understand the significance of the lattices? Well, let's go back to string theory 101, the perturbative quantization of the bosonic string. And here, this is all spelled out very nicely in Joe's book, of course, and I'm basically using his notation, so hopefully everything I say here maps modulo my errors to what you'll find in Joe's book. Basically, the idea is the following. Let's say we take, I'm assuming everybody has at least seen the basic flat space bosonic string quantization. If you haven't, hopefully this is reasonably self-contained, and the answer will be quite self-contained. We want to compactify the bosonic string not in flat space, but on a circle. So we're going to start in one circle, and then we'll generalize to more circles. The x coordinate, which is a function of sigma and tau, is now mapping us into a periodic circle, and therefore the string can not only have momentum, but it can wind around the circle, so we can have something not only linear in t, which is of course the motion of the string, but something linear in x, which tells us that the string is wrapped around the circle. That's the winding number. So the expansion of x will be the usual expansion in terms of oscillators with a w sigma, winding times sigma, plus momentum times tau. The momentum, as usual, is n over r. The winding is m, which is the winding number, times the radius. So we have these two pieces appearing in the expansion. We'll talk a little bit later about T-duality, which basically flips these two, flips momentum and winding, when we invert the radius of the torus. In this discussion, for simplicity, I'm taking alpha prime equals 1 until the very bottom slide, where I'll stick it back in where we want it, bottom of the slide. And so the idea is we can take this winding and momentum and rewrite them in terms of a left-moving momentum and a right-moving momentum, L sub r, L and L sub r, which multiply tau plus sigma and tau minus sigma. So these are just linear combinations of p plus and minus omega, p and plus and minus w. I've chosen the apparently slightly unorthodox normalization, L, which actually is still using the notation in Joe's book, although he uses the k's more, for the following reason. These are really momenta in the left and right directions. In terms of momenta, we like to think of these as putting back a square root of 2 here, so that the square root of 2 would disappear from some of these formulae. But the way we've defined it with this normalization, the L's live on a lattice. If we take L squared, there's an inner product given by the lattice U, which takes L left times L right. The inner product U will be defined in the PW space. So U equals 0, 1, 1, 0. P comma W multiplies on U, PW, to get to PW. the norm of L, which is L left squared minus L right squared, is equal to 2pw, which is this norm here. And this is just, if we multiply these guys together, this is 2mn, and therefore it's an even integer. So the point of this normalization is that L squared is going to be an even integer. Okay? Now, the next thing we do in perturbative string theory is we write down the mass shell condition. Mass squared is the momentum k mu, and we need the conventionally normalized k for that, which has the square root of 2. So that gives us the usual mass shell condition for the string in flat space, which is 4 times n minus 1 and 4 times n tilde minus 1, plus an L left squared or an L right squared times 2 in the two different sectors. So what this does is it gives us the possibility of additional massless gauge bosons at particular radii of the compactification torus. So the standard gauge bosons come from taking this mass formula, setting L left and L right both to 0, which is valid even if you don't compactify, and then we have to have n equals 1 and n tilde equals 1. So we have a state with no momentum, with alpha minus 1 tilde in, say, the mu direction and a compact direction. That would give us some gauge bosons, these gauge bosons 1 through 4. But another thing we could do is we can solve these mass shell equations by setting n equals to 0. By setting n equals to 0 and n tilde equals 1. So if n tilde equals 1, then the right moving momentum has to be 0, right? If n tilde is 1 and this thing vanishes, then Lr squared is 0, so therefore Lr is 0. But if n is 0, we have a 4 here, which can be canceled if L left squared equals 2. So if L left squared equals 2, we can get additional massless gauge bosons. This can happen. So Lr, remember, is this guy here. For Lr to vanish, P has to be equal to W. If P equals W, then LL is just P plus W over root 2. It's P squared plus 2PW plus W squared over 2. And looking at this formula here for P and W, this thing can be equal to 2 precisely when the radius in string scale units equals 1, so putting it back in the alpha prime, when the radius is at the self-dual point. So this is the perturbative string calculation that on a circle at the self-dual point, we get extra massless gauge bosons when in, say, the left moving sector, we get an L squared equals 2. Okay? So at the self-dual radius, this means that if we take, say, a type 2 string and we compactify on a circle of radius r equals square root of alpha prime, we're going to get extra massless gauge bosons, which enhance the U1 cross U1 to an SU2 cross SU2. We get W bosons, W plus minus, because we can have not only this solution, but we can do the same thing in the other sector. That's for the left-right symmetric bosonic string. So any questions about that? Probably everybody's familiar with that. I just wanted to go over it in detail because when we now compactify on a more general torus, we get, this was done by Narayan, we get a more general compactification on a lattice. And in general now, the momenta are going to live on a lattice gamma dd with signature dd. And if we get L squared equals 2, and L is completely either in the right sector or the left sector, we're going to get some enhanced non-abelian gauge symmetry. So what does this lattice look like? As I won't go through the demonstration, but as Joe argues in his book, modular invariance, and as was shown years ago in this Narayan context, modular invariance of the string worldsheet implies that the lattice on which we're compactifying has to be a unimodular or self-dual lattice. So we're compactifying on a unimodular lattice, gamma dd, which in this case then is just going to be d copies of u, basically, for a right-left symmetric string. And so the moduli space of compactifications is basically given by considering all the possible lattices up to choices of these radii and angles. So we have to basically look at the full moduli space of lattices where the inner product is defined through this gamma. And for certain choices of the moduli, we're going to have enhanced symmetries because we'll have a left-moving or a right-moving momentum, which will square to 2 and give us an extra massless gauge boson. So the heterotic string is basically defined by breaking up the right and left parts of the string into two different kinds of degrees of freedom. That's why it's called heterotic, hetero meaning different. On the right, so I'm going to use a slightly different convention. I'm going to vary from Joe's convention here and put the 26 bosons on the right moving sector and the 10 on the left, because that will fit in with a lot of conventions of lattices where we put the bigger number on the right. You could do the same thing and put the bigger number on the left, but I'm just going to use this to fit with the lattice notation. Joe, you look unhappy.
I spent months worrying about this, which convention, which is on the right and which is on the left hand.
I'm sorry. The reason I'm doing it is because in all the discussion of like K3, people always talk about gamma 319 and not gamma 19.3. Sorry about that, Joe. I actually spent a while going back and forth on this, and I was going to follow your convention, but then I was going to have to mess up all the discussion of all of the intersection forms on surfaces and things like that. And all the literature on intersection forms on the surfaces puts all the stuff on the right. Sorry about that. So yeah, I apologize. I'm also, for related reasons, I'm also using the plus minus 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 convention rather than the minus plus 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 convention, which Joe uses. That's, I think, the one place I'm consciously deviating from your conventions. Yeah, so in comparing everything here to Joe's book, just flip the right and left. Sorry. Joe, did you have a reason that you ended up with this?
No, I was trying to be compatible with the maximum number of papers at the time, and it was impossible to be compatible with everything.
Yeah, I'm sure that you were compatible with the maximum number of papers related to the heterotic string, but for the particular application I have in mind today, I want to put it the other way because of compatibility with other things. So yeah, sorry about that. Okay, but hopefully it won't be confusing. So now we can use this fact that we've just discussed the classification of unimodular lattices. The unimodular lattices in Euclidean 16-dimensional space, because if we just go to 10 dimensions, we're compactifying 16 right movers and no left movers. So we need to compactify on a lattice gamma 0, 16. So there are two possible lattices we could compactify on. We could compactify on E8 cross E8, or we could compactify on SO32 cross Z2, or on lambda 32. Yeah, sorry, I wrote it here. This is the lattice. This is the gauge group. We can compactify on E8 plus E8, or lambda 16, which gives us one of these two enhanced gauge groups. Because for these compactifications, since we only have right movers, all the points in the lattice are realized by right movers satisfying by L squared equals 2. So we get an enhanced gauge symmetry for all of these things here. So we get a whopping big symmetry. Let's go down by one dimension. In one dimension lower, we're compactifying the right moving bosons in 17 dimensions and the left movers in one dimension, thus on a lattice of gamma signature 117. And as soon as we go up one more dimension, the classification of unimodular lattices simplifies our life dramatically, because suddenly there's not two different lattices, but there's only one lattice. It's just one copy of U plus two copies of minus E8 with the minus sign because I've stuck them on the right. So that shows us that we get the same theory when we compactify E8 cross E8 and SO32 heterotic strings, even on a single torus, because they're equivalent to compactifying a theory on this lattice gamma 117, and there's only one such lattice. So what looked different in 10 dimensions becomes the same in 9 dimensions. Questions there? Okay. So what happens when we take the heterotic string? This was the question we wanted to answer that started us out at the beginning of this lecture. We compactify the heterotic string down to 8 dimensions. We're going to compactify on the lattice gamma 2, 18, which is U plus 2 E8s. There's an Orion moduli space, which is basically these are the linear transformations on the definition of the normalization of the lattice space. So I mean, these are linear transformations giving us the basis vectors of the lattice space. These are the symmetry groups under SO2 and SO18. And then there's a discrete symmetry group, which is the T-duality symmetry, which basically says for any given lattice there are discrete symmetries which leave the lattice unchanged even though they take one lattice vector to another. Those turn into the T-duality symmetries of the theory. The bottom line is we can take this compactification and by choosing the right movers and left movers, that is choosing the right moduli in this moduli space, we can enhance the symmetry beyond SO32 or E8 cross E8. We can get bigger gauge groups. Basically, we can get any gauge group with the property that the negative of the lattice associated with that semi-simple gauge group, where the factors are simply laced factors, embeds into the lattice gamma 218. So we have a precise mathematical condition telling us what gauge groups we're allowed to have. We're allowed to have any gauge group so that if you write down the associated lattice, that lattice admits a lattice embedding as a sublattice of gamma 218. So, for instance, Joe mentions in his book that you can get SO36 through this construction, which is bigger, obviously, than SO32. There's a nice work by Morrison and Seiberg where they show that you can get SU18 mod Z3 with a Z3 quotient. But basically, this is the important part of the lattice, which is the SU18, which is associated with the Dinkin diagram A17. This obviously has 17 generators, and therefore it's an enhanced symmetry that goes beyond the rank 16 Lie groups of SO32 and E8 cross E8. So you can get enhanced symmetry groups which are bigger than the heterotic symmetry group by this embedding, and this is the precise classification of what groups you can get. If you want to go a little further, this is the thing which I'm going to take and move forward with, this condition on embeddability of the associated lattice to a given group. But if you want to go a little further, there's actually some very beautiful work by Nikulin on lattice embeddings. He has given a set of necessary and sufficient conditions for one lattice to embed into another. And in general, the theories are a little tricky because the theorems are a little tricky because they involve a lot of number theory and p-adic stuff. But just to give you the flavor of some of what you can get out of these, let me give you a simplified version of one of his main theorems. If we have a lattice, an even lattice S of signature T plus T minus, and an even unimodular lattice T of signature L plus L minus, then there exists an embedding from S into T whenever the following conditions are satisfied. So certainly L plus minus L minus has to be congruent to 0 mod 8. That's needed for even unimodularity. The positive and negative dimensions in the signature of T have to be bigger than the corresponding dimensions in the signature of S. You can't embed something with 3 negative with a signature 3 comma something into something with a signature 2 comma something. And then you have to have the condition that the total dimension of the lattice you're trying to embed into T minus the total dimension of the embedding lattice S has to be bigger than the following thing: the minimum number of generators of the finite group that you get when you take the dual of the lattice S and you mod out by the lattice S. Remember, we had this picture here in one dimension. We had a lattice in one dimension with E squared equals 2. This lattice is Z, right? But the dual lattice has extra points, right? So if we call this lattice S, then S modded out by the dual lattice S star here is going to be Z2. So this is where his theorems get a little tricky. The precise conditions depend, in general, not just on this group and its minimum number of generators, but on the prime decomposition of the structure of this group. And I won't go into that, but I will just point out the following, that this condition tells you, among other things, that even the group SU19 is acceptable in 8 dimensions. Because if we take, that should be S. I'm sorry, it's S star slash S. I wrote it wrong on the board. This is S star slash S, right? Because S star is bigger than S. So S star slash S is a finite group. And there's a book by Conway and Sloan where you can look up what's called the glue group of various lattices. And for SU19, or A18. The glue group is Z19, and that's the cyclic group of 19 elements. And because 19 is prime, we're in good shape. There's only one generator of the cyclic group of 19 elements, and therefore this group, which has rank 18, fits just barely. We've got 18 is less than or equal to 18 here. The L here is equal to 1, and the difference in dimension is equal to 2. So we can squeeze in SU19, but we can't squeeze in SU20 because that has rank 19, which is bigger than the 18 of the negative definite part of the signature of the lattice. So again, you can go into Nikulin's work and find more precise conditions and figure out exactly which groups embed. But the takeaway message that I want to take from this analysis of the heterotic string in 8 dimensions is that the set of groups you can get is the set of groups where G where the associated lattice embeds into gamma 218. So that tells us what one picture of V is, right? We have V, the set of G, so that lambda G goes into gamma 218. And what I will do in the next lecture, at the beginning of the next lecture, before moving on to 6 dimensions, is we will start to talk about F theory, and I will show you how exactly the same condition comes out of F theory, so that we get precisely the same conditions and precisely the same moduli space, in fact, for the set of F theory compactifications to 8 dimensions. And I'm out of time, so I'll stop there and take questions. Yeah, sorry. Ignore the thing on the left for the moment. The SO218/R, that's a group. The slash of those, that's just the usual quotient by a group, by a subgroup. The convention is that when you then mod out by a discrete group, rather than writing another slash and then the discrete group, it's usually put on the left with a backslash, but it just means you first mod out by the continuous group, and then you mod out by the discrete group. Generally, that discrete group will be a T-duality or duality symmetry group of the theory, so that the things which you're identifying through that duality group will look the same, but they will look different from the point of view of the lattice, but they'll have the same physics. So that's the duality symmetry group. The simplest one is if you take if you compactify on a torus T1, right? Here's T1. We have a lattice that looks like this, where we have winding and momentum, something like that. This corresponds to the lattice where this has, something like this, where this has signature -1, 1 -1. Sorry, this is 0, 1, 1, 0, is the inner product on that lattice. There's a T-duality symmetry which exchanges those two things. So if we exchange winding and momentum, that exchanges those. That will exchange this to this. It doesn't look like a symmetry here, but it is a symmetry of the lattice and therefore a symmetry of the theory. That's where T-duality comes from. Good. Other questions? Yes?
For integrals on supergravity and E, do you need to have the gauge multiplets?
You need to have the gauge multiplets. Good. So the question is, could you have, you're saying if we go back to the beginning here, could you have a theory with just the supergravity and no gauge multiplets? Oops. Is that your question? Yeah. According to what we understand from supergravity, sure. There's no constraint which says that we can't have a trivial group. What we're going to see from string theory is that your group has to embed in this way. I thought I just wrote it down, but maybe I erased it. Your group has to embed into gamma, the lattice of your group has to embed into gamma 218. So it doesn't seem you can realize that in string theory. So the question I'm going to end with at the end of the 8D discussion is, can we find any better constraints from 8 dimensions that would rule out those theories? Because in fact, all the ones that are going to embed into gamma 218 are going to have a rank 18. You're going to have abelian, there's always 18 abelian generators. That's the 18 I put down is the fact that there's always 18 U1s, and then the question is whether you have a non-abelian enhancement of that. So all the theories we can get from string theory are rank 18, but there's no constraint that says that we can't have a rank 0 gauge group from the point of view of the low energy theory. So here there's a bigger disparity than we saw in 10 dimensions between the space G and the space V. That's part of the puzzle I'm going to leave you with next time. Yeah. Other questions?
The rank 16 should be minimal, right? Because after compactification on T2 may not be a unimodular lattice.
Now, you always get an extra 2 from the gravity multiplet, so you always get rank 18. There's no way that I know of to avoid a rank 18 gauge group in this theory. So you might imagine that there's a low energy constraint that insists that the rank has to be 18. But something like an anomaly condition, but not. Good. Okay, I will stop there for today, and we'll have more fun tomorrow.